Chlorofluorocarbon. Chlorofluorocarbons CFC and hydrochlorofluorocarbons HCFCs are fully or partly halogenated paraffin hydrocarbons that contain only carbon C, hydrogen H, chlorine Cl, and fluorine F produced as volatile derivatives of methane, ethane, and propane. They are also commonly known by the DuPont brand name Freon. The most common representative is dichlorodifluoromethane R-12 or Freon-12. Many CFC have been widely used as refrigerants, propellants in aerosol applications, and solvents. Because CFC contribute to ozone depletion in the upper atmosphere, the manufacture of such compounds has been phased out under the Montreal Protocol, and they are being replaced with other products such as hydrofluorocarbons HFC, including R-410 and R-134a. Structure, properties, and production. As in simpler alkanes, carbon in the CFC bond with tetrahedral symmetry. Because the fluorine and chlorine atoms differ greatly in size and effective charge from hydrogen and from each other, the methane-derived CFC deviate from perfect tetrahedral symmetry. The physical properties of CFC and HCFCs are tunable by changes in the number and identity of the halogen atoms. In general, they are volatile but less so than their parent alkanes. The decreased volatility is attributed to the molecular polarity induced by the halides, which induces intermolecular interactions. Thus, methane boils at 161 deg C, whereas the fluoromethanes boil between 51.7 Cf2H2 and 128 deg C Cf4. The CFC have still higher boiling points because the chloride is even more polarizable than fluoride. Because of their polarity, the CFC are useful solvents, and their boiling points make them suitable as refrigerants. The CFC are far less flammable than methane, in part because they contain fewer CH bonds and in part because, in the case of the chlorides and bromides, the released halides quench the free radicals that sustain flames. The densities of CFC are higher than their corresponding alkanes. In general, the density of these compounds correlates with the number of chlorides. CFC and HCFCs are usually produced by halogen exchange starting from chlorinated methanes and ethanes. Illustrative is the synthesis of chlorodifluoromethane from chloroform. HCCl3 plus 2HF HCF2Cl plus 2HCl brominated derivatives are generated by free radical reactions of hydrochlorofluorocarbons, replacing CH bonds with CBr bonds. The production of the anesthetic 2-bromomenes-2-chloromenes-111-trifluoroethane halothane is illustrative. CF3CH2Cl plus Br2CF3CH-BrCl plus HBr. Applications. CFC and HCFCs are used in various applications because of their low toxicity, reactivity, and flammability. Every permutation of fluorine, chlorine, and hydrogen based on methane and ethane has been examined and most have been commercialized. Furthermore, many examples are known for higher numbers of carbon, as well as related compounds containing bromine. Uses include refrigerants, blowing agents, aerosol propellants in medicinal applications, and degreasing solvents. Billions of kilograms of chlorodifluoromethane are produced annually as a precursor to tetrafluoroethylene, the monomer that is converted into Teflon. Classes of compounds. Nomenclature. Chlorofluorocarbons CFC. When derived from methane and ethane, these compounds have the formulae CClM-F4M-NC2-ClM-F6M, where M is non-zero. Hydrochlorofluorocarbons HCFCs. When derived from methane and ethane, these compounds have the formula CClM-FnH4Mn and C2ClX586XY, where M, N, X, and Y are non-zero. And bromofluorocarbons have formulae similar to the CFC and HCFCs but also include bromine. Hydrofluorocarbons HFC. When derived from methane, ethane, propane, and butane, these compounds have the respective formulae CFMH4, MC2, FMH6, MC3, FMHeight M, and C4, FMH10 M, where M is non-zero. Numbering system. A special numbering system is to be used for fluorinated alkanes, prefixed with Freon, R, CFC and HCFC, where the rightmost value indicates the number of fluorine atoms, the next value to the left is the number of hydrogen atoms plus 1, and the next value to the left is the number of carbon atoms less 1. Zeros are not stated, and the remaining Freon-12, for example, indicates a methane derivative only two numbers containing two fluorine atoms, the second 2 and no hydrogen 1-1 equals 0. It is therefore CCl2F2. Another equation that can be applied to get the correct molecular formula of the CFC/R/Freon class compounds is this: to take the numbering and add 90 to it. The resulting value will give the number of carbons as the first numeral, the second numeral gives the number of hydrogen atoms, and the third numeral gives the number of fluorine atoms. The rest of the unaccounted carbon bonds are occupied by chlorine atoms. The value of this equation is always a three-figure number. An easy example is that of CFC-12, which gives 90 plus 12 equals 102. 1 carbon, 0 hydrogens, 2 fluorine atoms, and hence 2 chlorine atoms, resulting in CCl2F2. The main advantage of this method of deducing the molecular composition in comparison with the method described in the paragraph above is that it gives the number of carbon atoms of the molecule. Freons containing bromine are signified by 4 numbers. Isomers, which are common for ethane and propane derivatives, are indicated by letters following the numbers. Reactions. The most important reaction of the CFC is the photo-induced scission of a CCl bond, CCl3FCCl2F, plus Cl. The chlorine atom, written often as Cl, behaves very differently from the chlorine molecule Cl2. The radical Cl is long-lived in the upper atmosphere, where it catalyzes the conversion of ozone into H2O. Ozone absorbs UVB radiation, so its depletion allows more of this high-energy radiation to reach the Earth's surface. Bromine atoms are even more efficient catalysts, hence brominated CFC are also regulated. Impact as greenhouse gases. CFC were phased out via the Montreal Protocol due to their part in ozone depletion. However, the atmospheric impacts of CFC are not limited to their role as ozone-depleting chemicals. Infrared absorption bands prevent heat at that wavelength from escaping Earth's atmosphere. CFC have their strongest absorption bands from CF and CCl bonds in the spectral region of 7.8–15.3, referred to as the atmospheric window due to the relative transparency of the atmosphere. The strength of CFC absorption bands and the unique susceptibility of the atmosphere at wavelengths where CFC, indeed all covalent fluorine compounds, absorb radiation creates a super greenhouse effect from CF, HFCs, HCFCs, bromofluorocarbons as F6 and NF3. This atmospheric window absorption is intensified by the low concentration of each individual CFC. Because H2O is close to saturation, with high concentrations and few infrared absorption bands, the radiation budget and hence the greenhouse effect has low sensitivity to changes in H2O concentration. The increase in temperature is roughly logarithmic. Conversely, the low concentration of CFC allow their effects to increase linearly with mass, so that chlorofluorocarbons are greenhouse gases with a much higher potential to enhance the greenhouse effect than H2O. Groups are actively disposing of legacy CFC to reduce their impact on the atmosphere. According to NASA in 2018, the hole in the ozone layer has begun to recover as a result of CFC bans. History. Carbon tetrachloride CCl4 was used in fire extinguishers and glass anti-fire grenades from the late 19th century until around the end of World War II. Experimentation with chloroalkanes for fire suppression on military aircraft began at least as early as the 1920s. Freon is a trade name for a group of CFC which are used primarily as refrigerants but also have uses in firefighting and as propellants in aerosol cans. Bromomethane is widely used as a fumigant. Dichloromethane is a versatile industrial solvent. The Belgian scientist Frederick Swarts pioneered the synthesis of CFC in the 1890s. He developed an effective exchange agent to replace chloride in carbon tetrachloride with fluoride to synthesize CFC-11CCl3F and CFC-12CCl2F2. In the late 1920s, Thomas Midgley Jr. improved the process of synthesis and led the effort to use CFC as a refrigerant to replace ammonia and H3, chloromethane CH3Cl, and sulfur dioxide SO2, which are toxic but were in common use. In searching for a new refrigerant, requirements for the compound were low boiling point, low toxicity, and to be generally non-reactive. In a demonstration for the American Chemical Society, Midgley flamboyantly demonstrated all these properties by inhaling a breath of the gas and using it to blow out a candle in 1930. Commercial development and use. During World War II, various chloroalkanes were in standard use in military aircraft, although these early halogens suffered from excessive toxicity. Nevertheless, after the war they slowly became more common in civil aviation as well. In the 1960s, fluoroalkanes and bromofluoroalkanes became available and were quickly recognized as being highly effective firefighting materials. Much early research with halon 1301 was conducted under the auspices of the U.S. Armed Forces, while halon 1211 was, initially, mainly developed in the UK. By the late 1960s they were standard in many applications where water and dry powder extinguishers posed a threat of damage to the protected property, including computer rooms, telecommunications switches, laboratories, museums, and art collections. Beginning with warships in the 1970s, bromofluoroalkanes also progressively came to be associated with rapid knockdown of severe fires in confined spaces with minimal risk to personnel. By the early 1980s, bromofluoroalkanes were in common use on aircraft, ships, and large vehicles, as well as in computer facilities and galleries. However, concern was beginning to be expressed about the impact of chloroalkanes and bromalkanes on the ozone layer. The Vienna Convention for the Protection of the Ozone Layer did not cover bromofluoroalkanes as it was thought at the time that emergency discharge of extinguishing systems was too small in volume to produce a significant impact, too important to human safety for restriction. Regulation. Since the late 1970s, the use of CFC has been heavily regulated because of their destructive effects on the ozone layer. After the development of his electron capture detector, James Lovelock was the first to detect the widespread presence of CFC in the air, finding a mole fraction of 60 ppt of CFC-11 over Ireland. In a self-funded research expedition ending in 1973, Lovelock went on to measure CFC-11 in both the Arctic and Antarctic, finding the presence of the gas in each of 50 air samples collected and concluding that CFC are not hazardous to the environment. The experiment did, however, provide the first useful data on the presence of CFC in the atmosphere. The damage caused by CFC was discovered by Sherry Rowland and Mario Molina, who, after hearing a lecture on the subject of Lovelock's work, embarked on research resulting in the first publication suggesting the connection in 1974. It turns out that one of CFC's most attractive features, their low reactivity, is key to their most destructive effects. CFC's lack of reactivity gives them a lifespan that can exceed 100 years, giving them time to diffuse into the upper stratosphere. Once in the stratosphere, the sun's ultraviolet radiation is strong enough to cause the homolytic cleavage of the CCl bond. In 1976, under the Toxic Substances Control Act, the EPA banned commercial manufacturing and use of CFC and aerosol propellants. This was later superseded by broader regulation by the EPA under the Clean Air Act by 1987 in response to a dramatic seasonal depletion of the ozone layer over Antarctica. Diplomats in Montreal forged a treaty, the Montreal Protocol, which called for drastic reductions in the production of CFC. On 2 March 1989, 12 European Community nations agreed to ban the production of all CFC by the end of the century. In 1990, diplomats met in London and voted to significantly strengthen the Montreal Protocol by calling for a complete elimination of CFC by the year 2000. By the year 2010, CFC should have been completely eliminated from developing countries as well. Because the only CFC available to countries adhering to the treaty is from recycling, their prices have increased considerably. A worldwide end to production should also terminate the smuggling of this material. However, there are current CFC smuggling issues, as recognized by the United Nations Environmental Programme UNEP in a 2006 report titled Illegal Trade in Ozone-Depleting Substances. UNEP estimates that between 16,000 and 38,000 tons of CFC passed through the black market in the mid-1990s. The report estimated between 7,000 and 14,000 tons of CFC are smuggled annually into developing countries. Asian countries are those with the most smuggling. As of 2007, China, India, and South Korea were found to account for around 70% of global CFC production. South Korea later to ban CFC production in 2010. Possible reasons for continued CFC smuggling were also examined. The report noted that many banned CFC-producing products have long lifespans and continue to operate. The cost of replacing the equipment of these items is sometimes cheaper than outfitting them with a more ozone-friendly appliance. Additionally, CFC smuggling is not considered a significant issue, so the perceived penalties for smuggling are low. In 2018, public attention was drawn to the issue that at an unknown place in East Asia an estimated amount of 13,000 metric tons annually of CFC have been produced since about 2012 in violation of the protocol. While the eventual phase-out of CFC is likely, efforts are being taken to stem these current non-compliance problems. By the time of the Montreal Protocol, it was realized that deliberate and accidental discharges during system tests and maintenance accounted for substantially larger volumes than emergency discharges, and consequently halogens were brought into the treaty, albeit with many exceptions. Regulatory gap. While the production and consumption of CFC are regulated under the Montreal Protocol, emissions from existing banks of CFC are not regulated under the agreement. In 2002, there were an estimated 5,791 kilotons of CFC in existing products such as refrigerators, air conditioners, aerosol cans, and others. Approximately one-third of these CFC are projected to be emitted over the next decade if action is not taken, posing a threat to both the ozone layer and the climate. A proportion of these CFC can be safely captured and destroyed. Regulation and DuPont. In 1978, the United States banned the use of CFC such as Freon in aerosol cans, the beginning of a long series of regulatory actions against their use. The critical DuPont manufacturing patent for Freon process for fluorinating halohydrocarbons, U.S. patent #3,258,500, was set to expire in 1979. In conjunction with other industrial peers, DuPont formed a lobbying group, the Alliance for Responsible CFC Policy, to combat regulations of ozone-depleting compounds. In 1986, DuPont, with new patents in hand, reversed its previous stance and publicly condemned CFC. DuPont representatives appeared before the Montreal Protocol urging that CFC be banned worldwide and stated that their new HCFCs would meet the worldwide demand for refrigerants. Phasing out of CFC. Use of certain chloroalkanes as solvents for large-scale application, such as dry cleaning, have been phased out, for example, by the IP Directive on Greenhouse Gases in 1994 and by the Volatile Organic Compounds VOC Directive of the EU in 1997. Permitted chlorofluorocarbon uses are medicinal only. Bromofluorocarbons have been largely phased out, and the possession of equipment for their use is prohibited in some countries like the Netherlands and Belgium from 1 January 2004, based on the Montreal Protocol and guidelines of the European Union. Production of new stocks ceased in most probably all countries in 1994. However, many countries still require aircraft to be fitted with halon fire suppression systems because no safe and completely satisfactory alternative has been discovered for this application. There are also a few other, highly specialized uses. These programs recycle halon through halon banks coordinated by the Halon Recycling Corporation to ensure that discharge to the atmosphere occurs only in a genuine emergency and to conserve remaining stocks. The interim replacements for CFC are hydrochlorofluorocarbons HCFCs, which deplete stratospheric ozone, but to a much lesser extent than CFC. Ultimately, hydrofluorocarbons HFC will replace HCFCs. Unlike CFC and HCFCs, HFC have an ozone depletion potential (ODP) of 0. DuPont began producing hydrofluorocarbons as alternatives to Freon in the 1980s. These included SUVR refrigerants and dimethyl propellants. Natural refrigerants are climate-friendly solutions that are enjoying increasing support from large companies and governments interested in reducing global warming emissions from refrigeration and air conditioning. Phasing out of HFC and HCFCs. Hydrofluorocarbons are included in the Kyoto Protocol and are regulated under the Kigali Amendment to the Montreal Protocol due to their very high global warming potential and the recognition of halocarb. On September 21, 2007, approximately 200 countries agreed to accelerate the elimination of hydrochlorofluorocarbons entirely by 2020 in a United Nations-sponsored Montreal summit. Developing nations were given until 2030. Many nations, such as the United States and China, who had previously resisted such efforts, agreed with the accelerated phase-out schedule. Development of alternatives for CFC. Work on alternatives for chlorofluorocarbons in refrigerants began in the late 1970s after the first warnings of damage to stratospheric ozone were published. The hydrochlorofluorocarbons HCFCs are less stable in the lower atmosphere, enabling them to break down before reaching the ozone layer. Nevertheless, a significant fraction of the HCFCs do break down in the stratosphere. Later alternatives lacking the chlorine, the hydrofluorocarbons HFC have an even shorter lifetimes in the lower atmosphere. One of these compounds, HFC-134a, were used in place of CFC-12 in automobile air conditioners. Hydrocarbon refrigerants, a propane/isobutane blend, were also used extensively in mobile air conditioning systems in Australia, the US, and many other countries, as they had excellent thermodynamic properties and performed particularly well in high ambient temperatures. 11-dichloro-1-fluorothane HCFC-141 has replaced HFC-134a due to its low ODP and GWP values. And according to the Montreal Protocol, HCFC-141 is supposed to be phased out completely and replaced with zero ODP substances such as cyclopentane HFOs and HFC-345a before January 2020. Among the natural refrigerants, along with ammonia and carbon dioxide, hydrocarbons have negligible environmental impacts and are also used worldwide in domestic and commercial refrigeration applications and are becoming available in new split-system air conditioners. Various other solvents and methods have replaced the use of CFC in laboratory analytics. In metered dose inhalers MDI, a non-ozone affecting substitute was developed as a propellant known as hydrofluorocarbon. Tracer of ocean circulation. Because the time history of CFC concentrations in the atmosphere is relatively well known, they have provided an important constraint on ocean circulation. CFC dissolve in seawater at the ocean surface and are subsequently transported into the ocean interior. Because CFC are inert, their concentration in the ocean interior reflects simply the convolution of their atmospheric time evolution and ocean circulation and mixing. CFC and its F6 tracer-derived age of ocean water. Chlorofluorocarbons CFC are anthropogenic compounds that have been released into the atmosphere since the 1930s in various applications such as in air conditioning, refrigeration, blowing agents in foams, insulations and packing materials, propellants in aerosol cans, and as solvents. The entry of CFC into the ocean makes them extremely useful as transient tracers to estimate rates and pathways of ocean circulation and mixing processes. However, due to production restrictions of CFC in the 1980s, atmospheric concentrations of CFC-11 and CFC-12 has stopped increasing, and the CFC-11 to CFC-12 ratio in the atmosphere have been steadily decreasing, making water dating of water masses more problematic. Incidentally, production and release of sulfur hexafluoride SF6 have rapidly increased in the atmosphere since the 1970s. Similar to CFC, SF6 is also an inert gas and is not affected by oceanic chemical or biological activities. Thus, using CFC in concert with SF6 as a tracer resolves the water dating issues due to decreased CFC concentrations. Using CFC or SF6 as a tracer of ocean circulation allows for the derivation of rates for ocean processes due to the time-dependent source function. The elapsed time since a subsurface water mass was last in contact with the atmosphere is the tracer-derived age. Estimates of age can be derived based on the partial pressure of an individual compound and the ratio of the partial pressure of CFC to each other or SF6. Partial pressure and ratio dating techniques. Safety. According to their material safety data sheets, CFC and HCFCs are colorless, volatile, non-toxic liquids and gases with a faintly sweet ethereal odor. Overexposure at concentrations of 11% or more may cause dizziness, loss of concentration, central nervous system depression, or cardiac arrhythmia. Vapors displace air and can cause asphyxiation in confined spaces. Although non-flammable, their combustion products include hydrofluoric acid and related species. Normal occupational exposure is rated at 0.7% and does not pose any serious health risks.